This is ComD 4000 Hearing Science. This is your guest lecturer, Dr. Peter Ivory. This is lecture slide set 12A, part 2, continuing with our introduction to topics in psychoacoustics. 12A, part 2 corresponds roughly to study questions 733 to 739. We will resume at slide 17 in the lecture 12A slide set. Here we are back at slide number 17. At slide number 17, we begin to discuss one of the main topics in psychoacoustics called sensitivity. Sensitivity basically answers the question of what's the least amount of something that a person can detect. So when we think of sensitivity, first of all, we're thinking about this basic idea of detection of something. So can we detect a stimulus? Absolute sensitivity refers to what's the least amount of a stimulus that we can detect. And when we think about this for the auditory system, we basically could convert this into what's the smallest or the least amount of sound pressure level. So in sound pressure level, we're talking about dBSPL, as you discussed in the acoustic section of this course. And this lecture set part 2 focuses primarily on some of the background involved in measuring absolute sensitivity. And the reason for this is because tests of absolute sensitivity form the basis of clinical audiometry. So again, it's partly that's the reason why, is that our basic hearing tests stem from these principal psychoacoustic measurements. So absolute sensitivity, what's the smallest amount of a sound pressure level that a listener can detect? This other type of sensitivity, called differential sensitivity, will be picked up more in part 4, I believe, of lecture 12A, lecturecasts, just dividing them up that way. And differential sensitivity is also very important because this answers the question, what's the smallest difference that somebody can detect? And in the literature and in your textbook, there's several other names for differential sensitivity. One of them is the just noticeable difference, and so therefore you might see this as a JND. Sometimes it's called a difference Lyman or DL. And so in any of those cases, those refer to the least amount of a difference that someone can detect. What will become important is to think about the three aspects of any acoustic stimuli. It's amplitude, its frequency, and aspects of its timing. And so therefore, what's the least amount of amplitude, what's the least amount of frequency, what's the least amount of timing differences that a person can detect? That also becomes an important characteristic when we think about the auditory system. So to focus on absolute auditory sensitivity, we're talking about what's the smallest amount of an acoustic stimulus in terms of its amplitude that a listener can detect. What we have to try to do is to make an estimate of what that sensitivity is. We have to sort of make a measurement and an estimate of that. And again, as I said on the slide prior to this, tests of absolute sensitivity are the basis for clinical audiometry. When we think about all of the factors that can influence a measurement, an estimate of absolute sensitivity, they include many things. On the next few slides after this will be material from your textbook that talks about some of what they refer to as the variability in human responses, and we could think of these as some of the factors that influence a measure of sensitivity. So what are some of the things that are important? And one of them would be stimulus calibration, whether or not the test equipment is appropriately calibrated. Again, the idea of acoustics provides us with a quantifiable, which is to say a repeatable stimulus. That's very important because that, again, provides for an elevation to a level of believability, and that's an important characteristic that acoustics provides to basic hearing testing. A second characteristic is a factor that will determine or influence an estimate of absolute sensitivity is how the stimulus was presented. And you will see in this slide set various different methods that will be referred to as methods of limits, methods of constant stimuli, methods of adjustment that are for lack of a better word, could be referred to as the psychometric procedure. In other words, how are we exactly manipulating the stimulus, and that might be referred to as the psychometric aspect of it. Another characteristic is listener response bias. Listener response bias addresses the likelihood that a listener will respond that they heard something even if they didn't, or the likelihood that a listener will not respond even though they did hear it. Those are listener response biases. Those will be covered more in depth in what's called the supplement to Lecture 12A under the topic of signal theory of signal detection, or theory of signal detectability, and that's covered in a separate slide set and lecture cast. Equipment used will have an effect. Specifically, if we're using an earphone on top of the ear, or if we're using a speaker, a loudspeaker, which is now providing sound in a sound field. What may become obvious to you, or what you should sort of immediately have an understanding of, is that when we're using a loudspeaker in a sound field, we are now providing stimuli to both ears. If you're using an earphone, the typical presentation in an earphone is to present to ears individually. So there's a distinction there. And then other test conditions. Otherwise, the background of noise and things like that will have an effect on any estimate of auditory sensitivity, and particularly absolute auditory sensitivity. On this slide and the next 5 or 6 slides, we'll review some material that's taken from the Emanuel and Letkowski textbook, and they describe these slides, or use as the header for these slides, reasons for variability in human response. That's a reasonable approach, I suppose, to think about it that way. We can think about them as sort of factors that will influence an estimate of sensitivity, as I did on the previous slide. In either case, these next 5 or 6 slides are important factors for you to contemplate, because they're going to be in play when you are learning about and are actually executing tests of hearing as part of audiometry. And that would be in the follow-up class to this, which would be ComD 4020, and that's audiometry. So hold on to these slides. I'm sure your instructors in ComD 4020 will comment on these variables as well. So the first set of things to contemplate would be instructions. Were the instructions provided to the listener clear? Were they understood? Were they in language and vocabulary that the person could understand? Did the examiner explain all pertinent parts of the task? Did the examiner's instructions provide any kind of bias to the observer, to the listener, so that they would respond in a certain way? And in fact, to some respect, the instructions are one of the primary ways that we can get a person to respond more or less, depending on how they're responding, depending on our instructions. That'll become clearer when we talk about the notion of theory of signal detectability. Second aspect in variability is listener bias. Listener bias has to do with whether the person is more or less likely to respond in this test condition. Anticipation. Does the person have this sort of psychological anticipatory response? You, as an initial or beginning hearing tester in your audiometry class, will no doubt set up a pattern of stimulus presentation that you will basically train your listener to respond, to provide what would look like a response, even though they might not have heard anything, simply because they anticipated that you were going to present a stimulus at that particular point. So they were anticipatory. So one of the challenges you will have as a beginning clinician and beginning hearing test person is to vary your presentation pattern so that you don't set up your listener to anticipate. It's sort of a general, sort of psychological kind of error is not exactly quite the word, but a condition that someone might be in. Reason number 4 from EL has to do with external and internal noise. So any noise that's in the environment, what they call external noise in the environment, they say noise from a fan or any other background noise, will affect the estimate on absolute sensitivity. And also any internal noise. This could be noise from your own breathing, from ringing in the ears that a person might have, and other sorts of noises that might be biological noises that might be affecting a test. Internal noise, breathing noises and things like that, true biological noises are going to tend to be more of a problem for people with very good hearing because they're hearing so much that they hear all the different biological things as well. Again, external noise is going to be more of a factor of room conditions. There's going to be some rooms and some environments where the test results will look like a person might have a mild hearing loss when in fact it's just simply the presence of the external noise that you had to now make the stimulus of greater amplitude to overcome the background noise. And if you didn't know that, you might come to the conclusion that the person has a hearing loss when in fact it was a noisy background. On most clinical tests of audiometry done by audiologists, they're done in rooms that are sound treated, so there's an absence of external noise, or at least a minimization of external noise. And that would be specified on the test form. If a test is done outside of a standard clinical audiometric sound-treated suite, there's usually something that the examiner would check off to denote what the background noise conditions were. The more noise, the more likely that those results are not showing true estimates of hearing because they're going to be influenced by the background noise. Attention has to do with, is the person paying attention to the task or not? Are they distracted? Are they fatigued? Any other variables that might have to do with are they in fact paying attention? One of the things that you'll have to just sort of take for granted for the moment, but you will experience when you are in your audiometry class and actually participate and get your hearing tested, when you're listening at the sound pressure levels that would elicit absolute auditory sensitivity responses. These are very, very soft stimuli. And you might even be, they're so soft that you might even fall asleep because the test is so subtle. And I'll leave it to you to have that experience, and hopefully you'll be paying attention when you're helping your classmates out to do their tests. Motivation. This has to do kind of with bias. In other words, does the person have a particular reason to want to do poorly on a hearing test? And you might think, why would somebody want to do poorly on a hearing test? Well, sometimes the outcome of a hearing test shows that a person might qualify for some kind of cash award or litigation or for example, a pension or a disability payment that might come from either Social Security or the Veterans Administration. So there's a lot of reasons why poor hearing and the results that would show poor hearing might have a cash money benefit to the person. Alternately, there are some people that when they're getting tested, they need to do very well in order to, for example, qualify for certain jobs. And so if you wanted to be, for example, in law enforcement, typically you have to have hearing that meets a certain standard. And if you fail to hear at those levels, in other words, your hearing is poorer than that, then you fail to meet the qualifications. This is true for some different types of jobs in government and And so, for example, the one that I'm most familiar with would be sort of in law enforcement. So LA Police Department, LA sheriffs have to meet certain standards in order to be accepted as a physical standard for those positions. And this last slide from the Emmanuel Natowski book talks about training. And so again, if a listener is trained to what the task is and has some practice runs, then they're going to be better off than someone who's not. And then they just say many other reasons, and I'll pick up on a couple of them as we sort of go through, and you will also get some of these when you are in audiometry. So you can see that the measure of absolute auditory sensitivity is in fact sort of complicated. And so always kind of remember those factors as sort of part of what are the challenges in actually taking that measurement. Let's take a couple of slides now to contemplate some of the theoretical aspects of sensitivity. Sensitivity, and particularly in this case we're focusing on absolute sensitivity, so the least amount of a stimulus that a person can detect, is really a property of that person. It's part of what we characterize as their organic capacity or their organic endowment. It's sort of saying that's their eyes are brown or their eyes are blue or whatever the case may be. That's a physical characteristic that they have. Absolute sensitivity and is again when we refer to this in hearing terms, hearing is something that occurs in the brain. And this sensation of absolute sensitivity, this capacity to respond to a very, very soft stimulus, we never really know for sure what's really happening at that moment of hearing. We don't really exactly know. We know there's neural firing, but we know that this is happening in the brain. But exactly what's going on at that point is sort of beyond our ability to measure directly. So the best that we can do is to manipulate the stimulus and observe a response and establish a relationship between the response and what is, in fact, the underlying organic property that we're measuring, which is to say absolute auditory sensitivity. And if you go back to slide 6, in the slides in the beginning of this slide set, that talks about some of those sensory principles. Let's see if I can find it here really quickly. So slide 6 in this slide set was that, and I'll quote, "Our understanding or quantification of sensory experience is based on our knowledge and measurement or quantification of the stimulus." So the way that we understand sensitivity is in the context of our knowledge of the stimulus. So based on the stimulus, which itself is measurable, that's what enables us to make a comment about sensitivity, because we can't really directly measure sensitivity because it's happening in the brain. And even if we could stick a needle or something in the brain to kind of measure neural activity in the part of the brain that's responding to sound, that doesn't still tell us exactly what that experience is that the person's having at that particular point. When we think about measures of estimates of sensitivity, we're looking at the relationship between the stimulus and the response, and therefore the characteristics of the stimulus are critically important. And again, that ties back to the comments that we've made to you, that's why acoustics is so important to audiometry and to the practice of audiology. Without the quantification of the stimulus, we really can't make any scientific and or clinical and or really critical statements about hearing. Again, one of the main characteristics of this quantification is that this allows people to utilize these measurements to make decisions that involve medical care, but sometimes surgery perhaps, or candidacy for hearing aids or other things. And the fact that these are reliable and valid measures based on a quantifiable stimulus makes this and elevates this to something that is a very believable sort of clinical discipline. That's a very important thing. And I know I keep saying it, but it is important. So since stimulus characteristics are so critical, anything that affects the delivery of the stimulus, and particularly if it's something that's unknown, is going to be a critical vulnerability and sensitivity. So audiologists and anyone that's doing hearing measurement really has to be on top of what the stimulus is, and to be sure that there's the stimulus that they're intending to deliver, that they believe that they're delivering, is in fact the stimulus that they are in fact delivering to the person. When we think of the basic hearing test, or basic test of absolute auditory sensitivity, a test of absolute auditory sensitivity manipulates a stimulus. Now, we talked about acoustic signals having three characteristics: amplitude, frequency, and time. And fundamentally, what you have to do in order to establish and measure absolute auditory sensitivity is you have to lock two of them down. Two of the acoustic factors have to be invariant across trials. And if they do, then we can make a comment about the other one, the third one that we're manipulating. So what we actually manipulate in a task of absolute auditory sensitivity is amplitude. We adjust the amount of sound pressure level in decibels. There's two kinds of decibels that we'll talk about. The decibels we talked about already in the course, dB sound pressure level, or a conversion of dB sound pressure level to audiometric decibels, which are dBHL. So when you use an audiometer, an audiometric test device, the dial there that's read in dB will show dBHL. And essentially, these can be measured in terms of dBSPL, but there's a table of values that adjust the actual physical dBSPL values to give you dBHL values. It's a mathematical transformation. It's the same. It sounds the same. It's just there's just a mathematical trick that we'll employ when we convert dBSPL to HL, and we'll talk about that in part 3 of this lecture slide set because it's an important mathematical transformation. So we have three characteristics of an acoustic signal: amplitude, frequency, and time. We manipulate one of those. We manipulate amplitude. That means that frequency and time, and in this case duration, have to be constant. And if they're not constant, then we have uncontrolled variables that will lead to other unpredictable, or what we might refer to as confounding effects. That was to say there's something else going on, but we don't know, we can't explain what that is. And one of them that we'll talk about in part 4, slide 67, is something called the time-intensity trading relationship. So fundamentally, and just sort of the teaser on this, is that below a certain amount of duration, you need additional amplitude in order to continue to hear it. The shorter that you make a stimulus, the likelihood increases you're not going to hear it unless you make it a greater amplitude. So there's this trade-off. You make it shorter in duration, you have to increase the amplitude. The shorter the duration, the more the amplitude, in order to maintain this constant sense of detection of that. This is only true up to a certain amount of duration. Above a certain duration point, it doesn't matter how long it's on. The time-intensity trading relationship would cease at a certain amount of duration of the onset of the stimulus. All right, the next few slides will review, and really the rest of the slides here in part 2 simply talk about some of the classic procedures that audiologists potentially could use to present the acoustic stimuli. And what we will, I'm going to present these three different kinds of methods that might be seen in an audiometric test environment. However, the one that is used, that is the method of choice in the procedures that are done in typical clinical audiometry, uses something called the method of limits. But we'll go through these others: method of adjustment, method of limits, method of constant stimuli. And at this point now, we're going to intersperse some of the classic slides with slides from the Emanuel and Latowski book. So, as just mentioned, these are all what are referred to as psychophysical methods, methods of adjustment, limits, and constant stimuli. Those are just the names for how do you present the stimulus. And the method of limits employs a sort of a set of rules for when you increase the amplitude and then decrease the amplitude until, we're introducing a word here that I haven't defined yet. We'll define this word in part 3, this word threshold. So for the moment then, we'll just say that threshold is for the moment, we're just going to say it's another word for the measure of absolute sensitivity. I'm going to make a distinction between threshold and absolute sensitivity that maybe your authors don't, but for the moment, let's just consider these as equivalent substitutes: measure of absolute sensitivity and this other word, threshold. All right, so in the method of limits, the stimulus, again, amplitude, because that's what's being changed, is the amplitude is going to be increased or decreased depending on the test sequence until you reach this point of the least amount of stimulus that the person can detect, because that's what absolute sensitivity is. Method of limits has been chosen for basic audiometric testing because it is effective from a time perspective and it's reliable. So those two things are important, that you can get the test done quickly but yet still maintain a reliable. In this case, reliability means repeatable. Is the test repeatable? And that's an important concept. The test, all other things being equal, if I do a test on somebody in New York City and all other things being equal, that there's no disease or change or anything like that, I should be able to have the person come to Los Angeles and do the same test on them and get the same results. And if that's the case, then those two tests were repeatable. One validated, if you will, the other one. So that's an important characteristic, is this test repeatability. All right, so we'll focus initially on method of limits, as the method of limits is the methodology that's used in basic clinical audiometry. Method of limits uses a series of ascending, and ascending means amplitude is increased, or descending, which means to say amplitude is less. We have less amplitude across trials. This is a figure that's sort of showing, here's a descending series, this is an ascending series, here's a descending series, here's an ascending series. It's hard to tell exactly what the pluses are aligned with here, because they don't seem to be aligned specifically with 15 or 20 or what have you. But we can at least have the gist here that, and let's just kind of say this arbitrarily like this, that stimulus at 20 decibels is presented, the person hears it. Stimulus is presented at, let's say, at 2 levels at 15, they hears, responds to both of those, responds once at 10, and now at 5 decibels and below, they're presented with the stimulus, but they don't respond. So there's a level at which, on the descending, we present 20, we present 15, we present 10, and the person responds to all those. When we present it at 5, they don't. So that's when they don't respond. On the ascending trial, then, the stimulus is presented at 0, at 5, they don't respond. It's presented at 10, and in fact they do. It's an ascending series. Descending, we present a variety. We present multiple stimuli. The person hears them till we get below 10, and then they don't respond. Here's an ascending series where we start at 0, present many at 0, many at 5, and when finally we get to 10, the person responds. So we've got this idea of descending versus ascending presentations. And as mentioned, hearing testing in audiology uses a modified method of limits. The way the procedure is written, and what we assume that most people would do, but at least the way that you will likely learn this, is that you begin with either a ascending or descending trial to find where you're going to start to focus on trying to find, again, this absolute auditory sensitivity. Remember, we're saying that's sort of the same as threshold. So in this particular task, and now we see a little bit better alignment here, we start with, again, this is an up arrow, so this is showing ascending. So these are all ascending trials. And so what we see here is that we start at 0 dB, no response, 5 no response, 10 no response, 15 no response, 20 no response, 25 no response. Finally at 30, the person responds. On the second trial, you start at 20, and you present. So you present at 20, they don't hear it. 25, they don't. 30, they don't hear it on that trial, but then you get to 35, and they respond. You go to trial 3, you start at 25, they don't hear it. At 30, they do. Here you start at 20, and then you go at 20, 25, they don't hear it. They present at 30, and then you repeat that at trial 5. There's a no response, and then at 30 again they hear it. So in this case, the signal intensity is manipulated until you get to a level at which the person responds. So let's walk through a modified method of limits, which, why it's modified is because we're going to be using a combination of ascents and descents to determine at what point we have the least amount of stimulus a person can detect. Now, from a clinical audiometric perspective, we only count, this is really a COMD 4020 point, we only count responses that are on ascending presentations, meaning when we're going from very, very soft to slightly greater amplitude. The actual psychometric movement on this is that anytime a person responds, so a yes is a response, a no would be a no response when a stimulus was presented. Every time that they respond, the next trial, we start it at 10 decibels less. Every time the person we presented and they don't respond, we get a no or they don't respond, the next trial is 5 decibels more. So let's walk through this, and you get a better sense, I hope, from the example as I walk through it. So on trial 1, we start at 0 decibels. We present it. The person does not respond. So what does the procedure say we do? We increase it to 5 decibels. What happens at 5 decibels? No response. What does the procedure say to do? You increase it by 5. We go to 10 decibels. What happens? No response. What do? Increase it by 5. We go to 15. We present it. No response. What do? You increase it by another 5. You go to 20, they don't respond. You go to 25, they don't respond. Finally, you increase it by 5 to 30, and what happens? The person responds at 30. So what did we say a moment ago we do? Once we get a yes response, what do? We decrease it on the next trial by 10. So where do we have a response? We had a response at 30 minus 10 gives us 20. So our next response should be, our next presentation should be rather at 20. So on trial 2, we readjust the amplitude, we set it down, and so now we present at 20, no response. With a no response, we increase it by 5 to 25, no response, increase it to 30, no response in this particular sequence, and then we increase it to 35, and in fact the person responds. After a response, after a yes, we drop it minus 10, so we go down to 25. So at 25 now, we present no response, we go up 5 dB, and again we get a response. What do? We go down 10, so we're from 30 down to 20. No response, go up 5 to 25. No response, and we go up to 30 and then respond, and then basically we just repeat that again. You go down to 20 again, no response, go up 5, no response here either, and then you go up and you finally get a response. So probably at this point we would say that the person's absolute sensitivity for whatever this frequency was in fact 30 decibels. It's not showing what kind of decibel it is, so we'll just say 30 decibels on that particular scale. As you will learn shortly, this word threshold has to do with a criterion value, and in this case we're saying that a threshold is the lowest level, lowest intensity or sound pressure level at which the response is found on 50% of the trials. So one of the hallmarks of threshold as a psychometric marker is that threshold, at least in audiometric testing, we have accepted this 50% response rate. And typically to establish a threshold, and again, threshold is just another sort of the mechanical words, if you will, the operational words for absolute sensitivity. So again, threshold and absolute sensitivity are clearly related, sort of slightly different theoretical aspects to them. And in order to do that, we need a minimum number of responses to find that. So if we're looking at 50% response rate, that would suggest that if we needed to have 3 responses at that level, that means we're going to have at least 6 trials in order to get a 50% response rate for 3 responses. Okay, there's another type of presentation called method of constant stimuli. Method of constant stimuli is kind of an odd name for this because the stimulus amplitudes are presented in either random or counterbalanced orders. They still can specify a threshold value as some kind of percentage response level. And as your authors point out, this is something that is typically used primarily in research studies because it is randomized and it is counterbalanced, and those are very important factors to minimize other kinds of variability that might occur in research studies. So the method of constant stimuli would be in probably any research article in which a threshold or a measure of absolute sensitivity was obtained. Not clinical audiometry. This would be more research audiometry. There's a third psychometric procedure called the method of adjustment. In the method of adjustment, the listener controls the stimulus until they hear it or they don't. And at this point, the threshold is taken as the mean value of several adjustments. There is a type of, in a sense, it's sort of like an automatic kind of procedure. Method of adjustment is probably reserved also for research applications, and it has a certain amount of time efficiency, but the listeners are involved in it, and again, for clinical testing, it would be problematic because they would be able to sort of manipulate the stimulus to demonstrate if they had a bias to show they didn't hear it, they could manipulate the stimulus so that it would appear like they had a hearing loss. You've seen this name before, I'm sure, Bekesi. Bekesi built an audiometer that had this automatic change. So as the person adjusted the a button on the Bekasi audiometer, it would set the stimulus down, and it would make it go then more greater amplitude until they heard it, and then the person would respond, and it would then adjust the level down, much like we just saw on this couple slides ago. But this shows is a constant up and down of the decibel value. And again, with the Bekasi audiometry, you would just sort of take the mean value as of multiple trials. But the listener is in control of this, and it's been a classic type of measurement, but really not one that's really utilized very much in basic clinical audiometry anymore. And that brings us to the end of part 2. And when we resume in part 3 at slide number 39, we will talk about the construction and the details of the absolute human audibility curve, which is these various amplitudes, the least amount of amplitudes, but displayed as a function of different frequencies to have a frequency-specific curve that we're going to look at that shows our species' ability to hear as a function of frequency. That'll be in part 3.